So we have these things called ions, and ions happen when atoms gain or lose electrons. Now, when an atom gains or loses an electron, if it gains an electron, it becomes negative because, well, electrons are negative. And so if you gain something that's negative, you're going to become negative. And so when we gain an electron, we have a negatively charged ion, and we call that a anion. And if we lose electrons, then the electron becomes positive because the nucleus is positive, and you have less electrons to balance out the positive charge of the nucleus. And so the ion becomes positive. And we call that a cation. Cation. Now, when I was in your position, I mispronounced it. I call it a cation, but it's pronounced cation and anion. Okay, and an example of an anion would be like chlorine minus, and we've always put the charge on the upper right-hand side. This is the charge. All right, it's always upper right-hand side. It's on the upper right. Okay, and now we have as a cation, we have an example would be like sodium plus. And once again, the charge is on the upper right-hand side. That's the only place you put it, is on the upper right-hand side. And so this minus on the chlorine means it's got one extra electron, and the plus on the sodium means it's missing one electron. Another example would be, say, oxygen 2 minus, or we could even say like aluminum 3 plus. Now, when I'm putting these charges on here, they're always on the upper right-hand side, and my preference is to go number first, then charge. In other words, 2 minus and 3 plus. But you could say, and you would not technically be wrong, okay? You do need to put the plus with the 3, though. Okay, even though, ordinarily we write them out. Now, the reason why I do that is when I see 2 minus, it's like I'm counting out 2 electrons, where if I see like a -2, I'm thinking like a negative number, like minus 2.3 or something like that. And to me, that's a number. It's a ordinary number, where when I'm doing it like this up here with the O2 minus, what I'm trying to emphasize is I'm actually counting them out. It's not an actual number which would have a decimal to it, because electrons only come one at a time. So you got 1 electron, 2 electrons, 3 electrons, or whatever. Okay, now what we need to be able to do is we need to be able to predict the charges. So we have to be able to predict charges. And what we do is we take a look at the periodic table, and the periodic table has a pattern. And I'm going to show you just a second. Periodic table. Okay, and the pattern goes like this, and I'm going to show it on the table in just a second, but it goes +1, +2, +3, -3, -2, -1, and 0. And this is the way it looks on the periodic table. I'm going to go ahead and pull up this periodic table so you can see. And so the pattern, everybody in group 1A is 1 minus. Everybody in group 2A is 2 minus. And we skip all of these guys because these are variable. And then we go 3 minus. Whoops. Oh, I'm sorry, guys. That's 1 plus, 2 plus, 3 plus. And then we go 3 minus, 2 minus, 1 minus, and 0. Never mind, I misspoke. So it was 1 plus, 2 plus, 3 plus, 3 minus, 2 minus, 1 minus, and 0. Okay? And what that means is that everybody here is plus 1. So when these guys, if they become an ion, they're all plus all the way down. And if these guys, if they do become ions, in other words, they're not neutral anymore, these guys are always 2 plus all the way down. Okay, same thing over here. These guys generally are going to be 3 plus all the way down if they become an ion, and 3 minus. Now, some of these guys can have different charges. Oxygen's always 2 minus, except when it's part of what's called a peroxide, in which case it's considered to have a charge of 1 minus, and all your halogens are minus all the way down. And of course, since the noble gases don't make any bonds most of the time, especially not ionic bonds, they're 0 all the way down. So the periodic table follows this pattern: plus 1, plus 2, plus 3. We skip over the transition elements, and then we go minus 3, minus 2, minus 1, and 0. Okay, and oftentimes we can express carbon as being plus or minus 4. And generally, if we're looking at ions, you have to look at what it's attached to decide whether it's going to be a plus or a minus 4. All right, so that's if you're making ions. Now, this is very different from covalent compounds. Now, to be an ion, usually, if the positive ions are usually metals, and the negative ions are usually nonmetals. Usually. So metals generally lose electrons to become cations, and nonmetals usually gain electrons to become anions. And to remind you, if you look at the periodic table, where are our metals and where are our nonmetals? If you take a look, everything to the left of that yellow zigzag line is a metal, all in here. These are all metals. And they generally become positively charged. And everybody here in green and pink is a nonmetal. And your metalloids it just depends. It just depends. All right. And so that's where your ions are. Okay. So you have negative ions, we call them anions. Now, how do we keep straight which one goes with which? And when I wrote this out, I deliberately wrote out the cation so that the T looks like a plus. So cation has a plus in it. Cation, the T, looks like a plus. And the anion, you can think of this as being a negative ion. See the A and the N, and then you got the ion. So a negative ion, anion. Cation goes with positive. So you have a positive in that cation. Now we have to be able to predict what the charges are so that we can make these things called ionic compounds. Okay, so we have ions, and then we have ionic compounds. All right, and then the number one rule for ionic compounds is that the net charge must be 0. Net charge must be 0. It's got to be 0. Okay. The reason is like this: if you have an ionic compound, it's a collection of positive and negative charges. And if you had a bottle of, say, nothing but sodium plus, without the negative charges to balance out that plus, well, positive charges repel, and a thing would just fly apart, and it would explode. As a matter of fact, you can do this with solid materials, or where you can hit it with a sufficiently powerful laser, knock off the electrons, and have what's called a Coulombic explosion. So what you need is you need to have net charge of 0 so that everybody, here's salt, sodium chloride, solid sodium chloride. For every chloride, we have a sodium. For every sodium, we have a chloride. And so that they're holding themselves together. And so the net charge, because of the arrangement of the crystals and the numbers, is 0 so it can hold together. Okay, so you have to have in an ionic compound, the charge has to be 0, the net charge. And the way we're going to ensure that is when we write out a compound. Here's our first compound. So we look at sodium and chlorine, and we look on our periodic table, and we're going to write out the compound. And so I look and I see that sodium is +1. It's over on the left-hand side. And I see chlorine is -1. And so we look at periodic table to get our charges, and we say plus and minus. There we go. And we're going to push these together to make a compound. All right, now we have to check, and we can't skip this step here. We have to check and make sure that the charges add up to 0, and they do. This adds up to 0. And so I see sodium chloride, and there's our compound right there. So we have sodium chloride. And we can do the same with something like, say, calcium and oxygen. What would be the compound that we would get here? And I look on my periodic table. I find calcium. I see it's in the 2+ column. I find oxygen. I see it's in the 2- column. And I go ahead and put the charges on, 2+, 2-, and they do add up to 0. 2 - 2 is 0. And so I can go ahead and push them together. And I have calcium oxide. There it is. Now, the problem arises is, what do you do if the charges are not equal? And let's say we have aluminum with oxygen. And I look on my periodic table and I find aluminum, and aluminum is in the 3+ column. And I see that oxygen is in the 2- column. And so I go ahead and write these down. And this does not add up. Matter of fact, 3 - 2 is +1. Okay, so that's not 0. That can't work. So we can't just push it together and call it a day. So what we do is we're going to do what's called crossing charges. And what you do is you go ahead and put them together and realize it doesn't equal 0. But what we're going to do is we're going to cross the 3, just the 3, not the plus, just the 3. And we're going to cross over to the oxygen. There it is. And then we're going to take the 2, not the negative part, just the 2, because we're doing counting, and we're going to cross it over to the aluminum. There it is. We're going to cross it over to the aluminum. Now, by doing this, we have ensured that the net charge will equal 0, and I can prove it to you. Now, one more note before I prove that to you. Notice that this is a subscript, and it needs to be off, low, and to the right. And this is a subscript. All right. Now, also, it represents the number of the atom. Okay, so that subscript green 3 means 3 oxygens. That subscript 2 to the bottom right of the aluminum means 2 aluminum atoms. Do not put the charge down there. That's not where the charge goes. Also, don't put no charge up here. No charges, all right? Don't put the charges there. This is the correct formula. Now, let's go ahead and prove that the charges do add up to 0. So if you take that blue 2, that means 2 aluminums, and each aluminum is plus 3. That gives me plus 6 charge carried by those 2 aluminums. And we take the 3 off of the oxygen. Each oxygen is minus 2. And so that means on the oxygens, all the oxygens together is minus 6. And if we add those up, well, 6 minus 6 is 0. And so sure enough, that's what we're looking for, and that's what we need. Okay, so we're going to cross charges if the charges are not already equal. Now, what we don't want to do is do like this, where let's say we had that original example of calcium ion, calcium cation, with the oxygen anion. Well, they already equal 0, so you don't want to cross. If you did cross, you would have this. But these are not the lowest possible numbers. And we need the lowest possible. So the lowest possible, we can divide everybody by 2 to get the lowest possible whole numbers, and then we can get calcium oxide. But the bottom line is if the charges are already equal, you just go ahead and push them together. You don't want to cross the charges unless the charges are different. And so we can do all sorts of stuff. We can do like, well, let's do calcium nitride. So we would have calcium, which is 2 plus, and we can have nitrogen. If we look on our periodic table, we find that nitrogen is in the 3 minus column. Right over here, it's in the 3 minus column. And so we would say 3 minus. And since they're not equal to 0, we're going to have to cross the charges. Go ahead and push them together, though, first. And of course, the 2 is going to cross down onto the nitrogen, and the 3 is going to cross over to the calcium. And see, notice that they are always, that subscript is low and to the right. And once again, we can say, 3 times 2 plus gives me plus 6 on the calciums. And we can say 2 times 3 minus gives me minus 6 on the nitrogens, and that gives me a total, so a net 0, which is exactly what we want. Okay? Now, it turns out that we have these things called polyatomic ions, and they look like this. First off, we have polyatomic ions, and we're going to get into naming in just a little bit, but I'm just going to show you how to deal with those. And so a polyatomic ion looks like this. It could be like a sulfate. You're going to have to memorize these, but that's a SO4 2 minus. Okay, and a polyatomic ion is a covalent molecule with a net charge. All right, and it looks like this. You got SO4 2 minus, you got, like, it's a sulfate, you got NO3 minus, that's a nitrate. More on naming this stuff later, but just to introduce you to the idea of polyatomic ions, we have these things like SO4 2 minus and NO3 minus, and they are on the back cover of your book, or at least they should be in the new edition. Yeah, under common ions. So these are back cover common ions, and you need to memorize that list of common ions on the back. Use flashcards or whatever you need to do. Naming is very important. And so we have these polyatomic ions, and so we can make ionic compounds out of these. Now remember, the net charge of the compound itself still has to equal 0. So there's some special things that you have to do here, but here's how it works. Let's say we have, say, calcium and say the nitrate. Okay, so there it goes. Now, if I just try to push these guys together, the net charge is not going to be equal to 0. The net charge in that case would be +1, because 2 minus 1 gives me +1. So how do we handle this? Well, we're still going to cross charges. There's an implied 1 here. There's an implied 1. That's implied. Okay, we don't usually put a 1 up there. But it's an implied 1. So this 1 is still going to cross over, but there's an implied 1 here as well. That's implied. We don't ever put subscript 1 there. But what about that 2? Okay, that 2 needs to cross over as well. But here's what we're going to do. We need 2 of everything here. So what we're going to do is we're going to put it in parentheses. We're going to put that polyatomic ion in parentheses, and we're going to put another subscript down here. And that's going to mean 2 of the nitrates, 2 of everything. Because you see that charge is on the entire polyatomic. It's not on the oxygen. And for Pete's sake, don't do this. Don't go NO6, 2 times 3. Don't do that. That changes what it is. And make sure that when you copy it down, it comes down as NO3 and not like NO. Once again, you're changing what it is if you do that. And so I can prove to you that that is the correct ionic compound between the calcium ion and the nitrate polyatomic. And of course, we have on the calcium, there's just one of them, times that 2 plus on the calcium. And I'm going to go ahead and put that in parentheses, +2. And we have, and that's +2. And we have 2 of the nitrates, but the charge on each one of those nitrates is -1. And so we get 2 times -1 gives me -2, and that gives me 0. So we're good. We're good on that calcium nitrate ionic compound. And we can continue on doing the same thing. Let's say we have, say, aluminum and sulfate, which is one of our polyatomic ions. And we would do the same thing. We would push them together. The charges do not add up to 0. So we need to cross charges. And of course, we'll take that 2, cross it over on the aluminum. There it goes. And we'll take 3, and we're going to cross it over on that sulfate, keeping in mind we have to put that sulfate in parentheses, the whole thing, SO4, the whole thing. And that means we have 3 sulfates with 2 aluminums. Keeping in mind that 2 minus charge is on the entire polyatomic. Okay? And so once again, we can check ourselves, and if we cross charges, we won't have to do it. But I'm just demonstrating to show you that if you have, say, 2 aluminums at +3 apiece, that gives me +6. And if you have 3 sulfates at 2 minus apiece, -2, that gives you -6. And so once again, we have a net charge of 0. So we're good. And so, and of course, if the charges are already equal, then you don't have to do any charge crossing. Let's say that we had, say, sodium and the nitrate ion. Well, they're already equal to 0, plus 1 minus 1 is 0, so we can just go ahead and push them together. And there's my sodium nitrate pushed together. And similarly, we could take, say, get out my periodic table here. We can actually pull together, say, magnesium. which is 2 plus off our periodic table. And if we had a sulfate that was 2 minus, then we can go ahead and push them together and call it a day, because 2 minus 2 is equal to 0. So now we can also pull these things apart when we do dissociation, and we're going to do that. And we have to keep in mind that when we dissociate these things, and we're going to do that in chapter 4, when we have aqueous chemistry, keep in mind, the atoms come out. And, polyatomics, you don't bust them up. You just go ahead and put the charge on there. And we could do the same thing over here. We take the aluminum sulfate, and if we were to dissociate that back into the ions, we would actually have 2 aluminums plus the 3 sulfates. Okay, whatever you do, don't bust these things apart when you go in the opposite direction, the polyatomics. Don't bust them apart. Okay, so putting these compounds together, the big take home on this is that the charges must equal 0. And if they don't, you must cross the charges. Keeping in mind, these polyatomics, after you cross the charges, you have to put it in parentheses if you have more than one. If you only have one, such as down over here, you don't have to put anything into parentheses. It's understood that there's just one. Now, these polyatomics, like I said, they are on the back cover of your book under common ions, and you do need to memorize that list. The reason is you're going to have, when we get into naming, and we're fixing to do naming, you have to be able to recognize that that's a sulfate. And you have to be able to recognize, for instance, that's a nitrate. Okay, so you need to memorize on the back cover your polyatomics, the name and the charge on the polyatomics. Okay, all right, so let's get into naming. How do we name these ionic compounds? There's a couple of different rules that you have to follow, and nothing beats practice. So let's just start with some simple ionic compounds. So we know how to make them, given the element and a periodic table and our patterns of charges. But how do you name them? So let's just start with this guy right here, NaCl. Now, I said NaCl just because I wrote it down, but I'm going to show you how to name these things. So don't call it NaCl. And you may already know what this is. It's called sodium chloride, and it's salt. And we all know what sodium chloride is. It's good on French fries. And so, how do we name this though? And the way you name ionic compounds is, first off, you have to decide, is it ionic compound? Because we also have these things called covalent compounds. How do we know it's an ionic compound? Because it's a metal with a nonmetal or polyatomic ions. Okay, so you have to ask yourself every time. Now, just because I'm doing ionic compounds, you got to ask yourself that every time. Okay, because the naming for ionic compounds is very different for covalent compounds. They're totally different. If you confuse them, you'll end up with, you'll get funny looks, and not only that, it'll be wrong. Okay, so how do we name this guy? Well, what we do is we name the metal. All right, you name the metal. What's the metal? Well, this is why you need to know where your metals and nonmetals are, is so that you can know whether it's a metal or nonmetal to begin with. And sodium is a metal. It's all the way on the left-hand side of our periodic table over here. There it is. There's sodium. Chlorine is a nonmetal. It's over here on the right-hand side. And so we name the metal, and the metal is sodium. All right. And the next thing we do is we name the nonmetal, and that is chlorine. And then we're going to drop the end. We're going to drop the end and replace with "ide." So this becomes chloride. And the "ide" is used when it's just the atom. Okay? So this becomes sodium chloride. Okay? And so you name the metal, sodium, you name the nonmetal, chlorine, and you drop the ending and replace it with IDE, so it becomes just the atom, just the atom. Now it's very different when we have the polyatomics are different. Okay, but this is just the atom. Okay, so we have sodium chloride for NaCl. What would we name this ionic compound? First off, is this an ionic compound? You would say, why, yes, it is. We have aluminum, which is a metal. We have oxygen, which is a non-metal. And so what we're going to do is we name the metal, aluminum. We name the non-metal, oxygen. We drop off the end and we name it oxide. Once again, we have "ide" on the end. Now note, do not use prefixes with ionics. In other words, this is not dialuminum trioxide, okay? No dies and tris and tetras and whatever, etc. Don't do it. Don't do it. This is not dialuminum trioxide. It's just aluminum oxide. It's understood there's 3 oxygens. It's understood there's 2 aluminums because we got those numbers from crossing the charges in the first place. Okay? And so we could have something like this. We could have, and we just named it's a metal with a nonmetal. Calcium's a metal, nitrogen's a nonmetal, and we would name it calcium nitride. There it is, calcium nitride. And so we keep, you just got to name them. You just got to figure out, if you have a metal with a nonmetal. Now, what do we do if we have a polyatomic? Now, this is why you've got to memorize your list of polyatomics on the back page, on the back inside cover of your textbook, is because you have to have sight recognition. So that if you see something like this, let's say, you have to be able to recognize that this right here is a sulfate. And polyatomics are generally are going to be ates and ites, with the exception being ammonium, which is it's got an on the end. Ammonium being NH4 plus. It's the only positive polyatomic is ammonium. All right. So you have to be able to have sight recognition that when you see an SO4, you know it's a sulfate, so that you don't do something like this where you say, and I'll see people do this, but don't be that person. I write things in red, sulfur tetraoxide or something crazy, I'll say something like that, and I'm like, no, don't do that. Don't do that. It's not sulfur tetraoxide. It's a sulfate. It's a sulfate ion. Okay, don't do this. Don't do that. Okay, so how do we name this? Well, you name it the same way. You name the metal. What's the metal? Calcium. And then you just name the polyatomic ion. And it is a sulfate, so we just say it's a calcium sulfate. You don't change the ending. when you're doing polyatomic ions, you do not change the ending, okay? And so we could have something like this. Let's change colors here. And so here's an ionic compound that is all polyatomic. And so let's do this whole thing is is two polyatomics, but ammonium is positively charged and it has a +1 charge. I'll just write that down over here for reference. And the phosphate has this is a phosphate, it has a 3- charge. It says that's where the 3 comes from, the ammonium. It's a polyatomic ion. You got more than one, you have to put it in parentheses. And so you name what you have. You name what you have. Well, that NH4, if you look on the back inside cover, that's an ammonium. So it's ammonium. And the PO4, that's a phosphate. And you just say ammonium phosphate. And this guy right here that I'm boxing in blue, that's your ammonium. And this guy that I'm boxing in green over here, the PO4, that's your phosphate. And so you name what you have when you have polyatomic ions. If you have a metal, you name the metal. If you have a polyatomic, you name the polyatomic, and you name it in order. And by the way, generally what we do is we usually put cations first, the positively charged portion, when we're naming them, and we put the anions second. Okay? Strictly speaking, if we were to write it as PO4 with the ammonium over here, and sometimes we might have a circumstance to do that. Strictly speaking, that's not wrong. It's just awkward. It's just awkward. It's not generally the way that you would see it. So you want the cation first and the anion second when you're writing out these compounds. And so a useful exercise that you can do on your own is you can list, say, some anions down on the bottom, cations down the left, and anions across the top. You can do this on your own, and you can try naming these guys. And so let's do that. And this is a useful exercise that you can practice on your own. Okay. And all right. And so you can just go ahead and cross the charges and do the name for each of these guys. Now, if we were face to face in the classroom, I'd actually make you come up to the board and do these. And I would say, what's the charge? Go ahead and cross them, and then write out the compound and the name. So, we have sodium plus and chlorine minus. Well, those charges are already equal. And of course, that would be sodium chloride. Name the metal, name the nonmetal, chop off the end, right? And now we have calcium 2 plus. We'll go top to bottom. And we have calcium 2 plus and chlorine minus. And what would you say? Well, the 2 would cross over onto the chlorine. And of course, there's a 1 on the chlorine. And so that would become calcium substrate chloride 2. And so this is calcium chloride. Chopping off that end, since it's just the atom, we're going to go iod all the way down. And similarly, we're going to cross that 3 over onto the chlorine, and this becomes aluminum chloride. Might not have given myself quite enough room, but notice, there's an iod on the end of all these chlorides. Okay? And so we can go to the oxygen and the sodium, and we would have the oxygen, the 2 would cross down on the sodium. This is important. You got to cross the charges to get them to equal 0. So it'd be sodium subscript 2 O, and we name the metal sodium oxide. And moving on down, the 2 and the 2 on the calcium and the oxygen are already equal, so we just push them together, and this becomes calcium oxide. And I'm going to move a little quicker here. And so the aluminum gets the 2 from the oxygen, and the oxygen gets the 3 from the aluminum, and we have aluminum, name the metal, oxide. And finishing up this last column, we have sodium subscript 3. It picks up the 3 from the nitrogen, and then we just cross over the nitrogen, and this becomes sodium nitride. And calcium and the nitrogen, they cross charges as well. So we got the calcium subscript 3 from the nitrogen. And then on the nitrogen, we have subscript 2 from the calcium. So we have calcium nitride. And then finally, we have the 3 on the aluminum is equal to the 3 to the minus 3 on the nitrogen. They add up to 0. So we have just aluminum with a nitrogen on it, and that becomes aluminum nitride. Okay, and in all cases, we are taking our anion part, and since it's just the atom, we're going to have an "ide" on the end. And this is an exercise that you should do on your own, so that you can have practice with writing out the appropriate chemical formula and writing out the appropriate name. And we can do the same thing with polyatomics. We could have, and I'm just going to do a couple here because I'm going to wrap it up in just a second. And so we can do naming with polyatomic ions, and we can do, like, I'll just do a 2 by 2 this time, like ammonium. And let's say we had, say, let's do aluminum 3 plus. Let's say we have these 2 cations, and let's say we had, say, a sulfate over across the top, and let's say a phosphate. Okay, and we can do the same exercise. I'm just going to do a 2 by 2 for interest of time, and you can do the same exercise. And NH4 is ammonium, and SO42 minus is phosphate. I mean, SO42 minus, pardon me, is sulfate. I was looking at the phosphate. And so they are, so the charges, you have to cross them over. And so the 2 is going to cross over on the ammonium. And since there's more than one of them, you have to put the ammonium in parentheses. And there's only one that crosses over on the sulfate. So this becomes ammonium sulfate. Notice the 8. And looking over on the right-hand side, we'll do the same thing. We'll cross over the 3 from the phosphate onto the ammonium. So we have 3 ammoniums. Notice that 3, you don't change that 4 on the H. It's an NH4 as an ammonium. 3 comes down on phosphate, and once again, we only have 1 phosphate. And so this becomes ammonium phosphate. Notice the 8 and the ammonium. And we can do the bottom one where we have aluminum cation, or just aluminum ion. And the 3 crosses over on the sulfate, and the sulfate's 2 crosses over on the aluminum. And so we say aluminum subscript 2, and then we have 3 sulfates. So we go SO4, 3. There's 3 sulfates. The 3 came off the aluminum. And so we have, name the metal, aluminum, and that is a sulfate. And then finally, the 3 and the phosphate, the 3 on the aluminum and the 3 on the phosphate add up to 0. And so we just push them together. And this becomes aluminum phosphate. And there it is. Okay. So like I said, this is a useful exercise for naming. A useful exercise for naming. And we can go in the other direction as well. If you're given something, you have to, when we're going in the other direction, you have to know the charges to be able to figure out what you have. And so if we had, say, aluminum with a nitrogen, how, that would be aluminum nitride. But let's say that you had, say, sodium, the name, sodium phosphate. You should be able to get the formula out of this. And the way we're going to do that is you go to the periodic table and you see that sodium is in that +1 column, and you have to memorize your polyatomic ions on the back page of the book, and you would write down PO4 3-, and then you can go ahead and cross charges, okay? And you get sodium 3, PO4, and there you go, you got sodium phosphate. So whatever you do when you're going in the other direction, never skip this step. Okay, never skip this step when you go back the other direction. Okay, so for the next WebEx, which I'm going to do on Friday, we'll continue with more naming, or for next time. I shouldn't say a specific day, but for next time, we'll continue with ions that have variable charges, things like iron 3+ and iron 2+, and then we'll do more naming, and then we'll do covalent compounds. So that's what we'll do for next time.